Okay, and we should be live.
Okay, thanks, Torsten. Thanks, everyone. Sorry for the 7-minute delay. We had some issues setting up the live stream, so everything should be on track now. So welcome to the 4th workshop on long-term visual localization. And first of all, a welcome from the long list of names here who are the organizers. And we hope we enjoy today's session. I know it's a bit challenging with time zones in 3 different major places in the world and 3 different, completely different time zones. But yeah, we should be able to keep it, I guess, interesting for everyone. First of all, some information. This is a live stream on YouTube in case you're in the Zoom room and you want to move over to YouTube. This is also what we will be using to monitor questions. So there's the live chat option there, and it's yeah, if you want to ask any one of us or a speaker a question, please post it there. And this is a website on the bottom where you could see the full schedule and some more information about the workshop, the organizers, the challenges, and so on. So this is the schedule. This is in Montreal time, so you should be able to quickly, I guess, convert based on the current time in your time zone. So at 2:15, we'll get an invited talk from Margareta Klee. 2:45 from Johanna Wald. 3:15 we'll do a short break, and then we'll hear from the winners of the 3 challenges. And then we come back with 2 more inviting talks. From Hongdong Lee and Michael Milford. So yeah, let me quickly try to recap what is new with respect to the challenges for this year. Challenges 1 and 2, this year we had 3 challenges, which is a change from the previous version of the workshop. Challenges 1 and 2 focused on the classical visual localization 6DoF accurate camera pose estimation. But with a change that we grouped for this year, indoor and outdoor scenes, and then we had 2 versions, sub-versions of the same challenge. So for the indoor datasets, we had some new, very interesting datasets like Gangnam Station. We had Inlock, Rio 10, and the new dataset from ETH and Microsoft. For the outdoor, we had 3 that were already used last versions, also like Aachen Day Night, Robot Car, Silda Weather, and also ETH's Microsoft there. So as I said before, this version of the challenge focuses on the problem of developing a full visual localization pipeline that takes an image and returns a full, very accurate 6DoF camera with respect to the predefined pre-built map. All datasets are available in capture format, and the results were evaluated using 2 evaluation servers. One is the visuallocalization.net and also the Rio 10 server. The leaderboards for both challenges are created based on the results from the individual tasks, and for the final ranking, we use the Schulze method. For more details, please check the website where you could see specific numbers for each task and for each method, and many more information. So yeah, let me announce here winners for the challenges 1 and 2, which are actually the same winners for both. So it seems like there's no huge difference between indoor and outdoor, and the same methods work quite well in both. So for number 1 winner, we have the Meglock team from Peng et al. And runner-up, we have the O-Space team from Gao et al. So congratulations to the winners for challenges 1 and 2, and we have talks coming later on where they describe a bit more how they achieved that. Challenge 3 is a slightly different version of the problem, and it's basically place recognition problem. And this was based on Mapillary street level sequences dataset, where it has more than 1 million images, and the images are tagged with GPS information. And we have different weather, different cameras, and different light conditions. And the difference here is that we don't really focus on very accurate pose estimation, but mostly place recognition. So a binary yes/no choice with respect to making a decision if this is the same place with another place we're looking. So this is based on single image retrieval, and the metric that was used was the Recall 5. Around 30 participants for this challenge, and we have a new high score. And you could see here the high score distribution or the graph that shows the evolution per day. And for the challenge 3, we have again 2 winners. First is the team from MEGVI, from Zhu et al. And second place is the team from University of Groningen with Leiva Valina et al. And the respective scores, you could see them here. Again, more information you can find on the website of this. Now let's move on to the first of the invited talks, which I'm sure it will be very interesting, and it will be from Margarita Kli from ETH. Welcome, Margarita, and really glad to hear you here.
Okay, thank you very much, Vasilia. I think you need to unshare your screen such that I can share mine.
Okay, 1 second.
Yes. So here we go. This should work. If not, please say something.
Yes.
Great, fantastic. So hello, everyone. Thank you for the invitation. My name is Margarita Kli. I am a professor here at ETH Zurich. I lead the Vision for Robotics Lab. And I wanted to talk to you about advancing vision-based robotic perception. Let me start my timer before I forget. Right, so why advancing? Because I think we've come a long way so far. And the question is where we're going, right? A big question. So in my work, I look a lot towards nature to get some inspiration. And I wanted to show you 2 videos. Here's one example where this eagle is reaching out to grasp salmon, seeing through water, planning its path such that it can grasp it while they're both in motion. Which I think is quite a spectacular example of visual perception. And this video here, where you can see a flock of starlings that they're moving in seemingly perfect unison without crashing into each other, at least not visibly, and coordinating to create these beautiful formations. And the question is, what kind of level of skill and situational awareness do we need to build into our robots to be able to navigate so seamlessly and interact with the world around us? So I've taken this big question and I've partitioned it into 3 distinct challenges. So forget about the challenges that Vasilios just talked about. This is now my 3 challenges. This big question, again, into 3, naively split into 3 challenges. So firstly, we need to equip our robots with high fidelity eco motion and scene estimation to get this basic perception of where they are and how they move in space. And then start building on top of that to have some richer scene representations such that our robots can reach out and grasp an object or actually complete the loop of navigation with path planning to do some autonomous navigation. And then on top of that, when we have robots able to address challenge 1 and 2, we would love to be able to exploit the fact that we might have multiple agents in the same space, hopefully cooperating to perform a common task together. And we're going to look at some examples later. So basically, I'm using these 3 challenges as bookkeeping within my talk, and these represent the 3 main research areas in my lab. I'm going to go through them and give you a taste of some of the works that we are doing. Of course, we can never say that one challenge is completely solved, but of course, some are more mature than others. So let's start by high fidelity ego motion and scene estimation, which it should be no surprise to this audience that is basically about high fidelity SLAM, right? Simultaneous localization and mapping. Now, here is a video from, it's getting very old now, it's 2012. It was during my postdoc years here at ETH, where we demonstrated for the first time that it is possible to automate the flight of a small aircraft, like the one you've just seen before, using a single camera, downward-looking camera. You can see there it's depicted. It's the drone is carrying it, and an IMU, an inertial measurement unit. So now, in order to create a video like this that looks, so back in the day also looked very nice, I have to say that we had to go on site 2 days in advance to calibrate our cameras, to make sure there's enough features around, we're flying at the right height, right? So there's a lot that needs to happen before we are enabling this autonomous flight. So you can see where I'm going with this. So there's a lot of problems, were a lot of problems back then that we needed to deal with. And fast forward a few years down the line, this is my student. She's holding a visual inertial sensor, basically using one camera and one IMU. And she's walking down a street in downtown Zurich, running OGVIS, which is a visual inertial slam pipeline. You can see the trajectory being estimated in red and the map points there in yellow and orange. And she's walking down one side and coming back up the other side of the street. And of course, these two locations should correspond to each other. And what happened here is that we have the inevitable drift. So no matter how good your SLAM estimate is, if you're not using some global localization, for example, from GPS, then you have to deal with this problem. And I guess the ones who participated in the challenge know exactly what I'm talking about. And we know how to address this in the community by basically building a vocabulary of visual words usually, and doing a similar search that Google is using for images. Now, the problems that we have when we're using vision, of course, is the problem that different places can appear to look the same. The same place can appear to look very different or somehow different between visits, and very different when you're considering the course of time, either in the day or day-night, or actually through seasons, right? And on top of that, if you are navigating the scene with an agile platform like a drone, then you also have to address the viewpoint changes. So looking at the same place from different viewpoints, how can you figure out whether you're in the presence of the same place or not? And let me focus a little bit on this last challenge. Let me say, first of all, that it's the whole problem is rather difficult, and usually in the literature, we isolate one or the other challenge, right? But what we really want is to address all of them at once. But let me focus a bit on viewpoints. So just to show you one example of a system that Fabiola came up with, she was trying to make use of the fact that SLAM is running anyway. And so on top of the appearance checks that we traditionally use for place recognition, she was also storing not only the local visual appearance, but also a local 3D map that came from SLAM. And using this local SLAM map, we used to test for geometric checks on top of the appearance checks to clean up some of these appearance matches. And so we used 3D and 2D checks from 2D landmarks to the 3D map that was being built. And you can see now the trajectory in blue is Fabiola walking down the same street a few months later, I think about 6 months later. And there's a green line appearing every time we are detecting a loop. We are not addressing all of the challenges here. For example, you can see some pedestrians and some illumination changes, right? Some logos have even changed their displays, and some stores have changed their displays and their logos, which made it very hard also to basically label, even for manual labeling. But this pushed us further to say, right, so if we really want to have wider baseline place recognition, with that system, we couldn't really push up to, for example, 45 degrees, as you see here, so from 0 to 45 degrees. And in order to be able to quantify this, of course, we worked with synthetic datasets, photorealistic synthetic datasets from real images that we construct here. So you can see the different angles that we have been working with. And she basically said, well, not only her, but together with other researchers in my lab, to take this system as we had it before, but then actually locally perform some map densification in order to enable more reliable and more extensive geometric checks to be able to recover from such wide baselines of 0 to 45 degrees, for example. And here you're going to look at some results from these synthetic datasets. We start with the Lagu dataset, which is planar. So we are localizing against the blue trajectory is the current trajectory, is localizing against the reference one, which is in red. So red is in 0 degrees, and then blue is back in 45 degrees to show you the most extreme changes in viewpoint that we've been addressing. Here is a more three-dimensional structure, which is much more closer to reality, right? So we don't have this planar, easy piece of cake to work with. And we tried also to simulate the type of quality of images that we get from, the monochrome images in reality. So we have both simulation results to be able to quantify how well we're doing, and actually we recorded better recall for perfect precision with respect to the state of the art for these 45 degrees viewpoint changes. But we also have real data as well. Just to give you a small taste, we also worked a little bit with learning-based place recognition for situational and illumination changes. So here we used webcam data from taken in June and taken in February. So webcam data from the same locations, right? So we taught our CNN to basically, it learned whatever we gave it, and it was able to successfully suppress, in most cases, the transient information in the scene and focus on what makes a place distinctive with respect to other scenes, but also being able to recover the query image with respect to what the system was shown before. Right, for the first challenge, basically, for high fidelity SLAM, we've been experimenting with different sensors. I didn't mention, but of course, we're working with different sensors like the event cameras, with sensor fusion, with deep learning, with place recognition, so many different areas to work on. And the reason for this was to come up with a backbone of the awareness of space for a robot, right? To give it a sense of where its pose is within a map of the surroundings, right? Building a map of the surroundings. And the key word here is that this map so far has been pretty sparse. And this is now my ball to the second challenge, which is about creating richer scene representations such that our robots can interact with the environment to reach out and grasp an object, or to avoid obstacles while flying, as in this work here. So here we're working with one camera only, and we are coming up with this grayscale 3D reconstruction that you see on the right-hand side, and we superimpose it against a laser scan that we took earlier on. This is shown in red, basically to quantify, qualitatively, to show how far the reconstruction is from ground truth, laser ground truth. Here we are using seeds of depth, for example, coming from SLAM, from a sparse SLAM map. And then we're using learned depth association or associations of the hue, right, of the pixel hue with respect to the depth, and to dilate these depth seeds. And we are able to come up with such reconstructions, but also with a confidence map of how confident we are within for each depth. And of course, you can see there that that's far from perfect, especially around windows, where we know that we wouldn't be performing that well, specularities, right? And it is with maps like this, so denser maps, that then we can show some autonomy happening. And here is a drone that is trying to plan its path autonomously around this scene of rubble. And the instruction that is given the drone is to come up with as good and complete reconstruction of this scene as possible. And what it is doing, it's using now a gimbal. So we have a gimbal and a camera, and we're evaluating different viewpoints around the current viewpoint, and we are selecting, so you can see them, the evaluated viewpoints in the surroundings of the drone. They're colored according to their information gain, their expected information gain. So green means good, let's go there. Red means probably you're not gonna get much for your effort there, so maybe avoid that. And just to tell you a little bit about how it works, I think it's better if I let Yves explain it as he did in his video just for a minute.
We present a path planner for 3D reconstruction of large scenes for an MAV equipped with the gimbal actuated camera. Potential next best views are sampled from the MAV's configuration space and ranked by their expected information gain. The information gain of a proposed viewpoint is calculated with the raycasting operation and encodes visibility of frontiers, visibility of unknown space, as well as quality improvements of the reconstructed surface. In this more intricate bridge scene, the actuated gimbal seems to be necessary to fully reconstruct the scene. Without the gimbal, the underside of the bridge is not fully absorbable, leading to gaps in the mesh. Our planners also perform well in large indoor scenes. Not only is our approach faster, but once again, some surfaces are only observable with the actuated gimbal.
Yes, so of course the gimbal can make a big difference, right? Because you don't necessarily need to move to a particular, to a different pose. You don't need to move your camera to a different pose to be able to see under the bridge, as you saw in these examples here. But generally, we have experience with and without the actuation in the gimbal, and we show very good results with respect to the speed and the reconstruction quality that we're able to achieve. In this paper, it was in simulation, but as you saw in the video before, we also run it with real scenes as well. Now, in another piece of work, so Luca here is has been working with semantics, right? So this is following the trail of thought that says we start with the basics. Let's assume that SLAM works well. So how can we have our drone that is effectively reaching a particular goal, moving from A to B, right? And then how can we use semantics, right, to help minimizing errors in the visual odometry? So we want to go from A to B. How can we use the fact that we know that there's roads, there are trees that move, or cars on the roads, or maybe terrain that is rather static. So it's a good source of static features. So in his system, Luca is using a deep reinforcement learning with deep policy training that is essentially trying to maximize the reward in an episode-based fashion. And it's using these three basic ideas that we want to maximize the reward of the survival of our visual odometry. So really keeping within the field of view landmarks that are predicted to give us good estimates, right? So and avoid areas where landmarks are not predicted to be that stable, for example, on top of water, right? We want to give a high reward for decisions that minimize the root mean square error, because for this training we're using unity-based simulated environments where we have ground truth versus visual odometry estimates, and of course a reward that is based on how much progress we are doing towards reaching the goal. And so I'm going to show you just visually some examples of the simulated environments and experiments that Luca has been working on. So here's an example of the real life scene, and we used photos of these to come up with a photorealistic view of that scene. And here you're looking at 4 different algorithms. The proposed is on the bottom right, and now also different experiments. But basically the bottom two methods are using semantics. And on the top, basically, we have no semantics. So we are the method is doing a lot of large detours. The success rate is low, and the estimation error is also high. Whereas when semantic, so on the right-hand side is the reactive planner that is trying to go for the shortest path to the destination. And on the bottom, on the bottom left, we have semantics that is only classifying this binary safe versus unsafe areas. And on the right-hand side, we have all the different colors of importance, all of the different basically importance weights of how useful a semantic class is towards reaching the visual odometry goal and achieving the best reward. And in this case, we can show that this way of dynamically adapting the importance of the semantic classes at runtime, it can make a real difference on basically the success rate of reaching the goal and the estimation error when along the trajectory. Right, so once we are dealing with, once we assume that we have dealt with challenges 1 and 2, let's look a little bit at multi-agent robot collaboration. And here is an example where we have a system of 3 drones. They each independently run SLAM on board. In this case, it's monocular SLAM. And they keep running their own estimates independently, but because resources are limited, in order to keep running at real time, at some point they need to forget about the past in order to be able to process the current view in real time. So before they forget, we, in the system that we created, CCM SLAM, which is also open source, we have a desktop computer, or actually it's a laptop computer here that acts as a server. It could also be the cloud. And the server is acting as this bookkeeping entity that is gathering information from all the agents. So the agents are dumping all their experiences to this server, basically key points and trajectory estimates. And then the server, which can have a much bigger set of resources, it can also run place recognition to merge the trajectories from 2 different agents and also optimize to the bundle adjustment and then inform any participating agents. And essentially, this central server acts as the hub that enables the collaboration between these agents in this centralized collaborative SLAM system. And worst case scenario, when there is no communication between the agents and the server, it means that each agent is running independently their own estimates, but best case scenario, they're actually sharing information through the server, sharing map points through the server, and collaboratively building a map of their environment. Now, we've taken this and also tried it with different platforms, and then also augmented it with inertial measurements as well, using very similar architecture and setup, but now with the inertial, we have metric scale gravity alignment that can enable basically autonomous flights. And just to show you some, give you an idea of some benefits of collaboration, which in effect they are straightforward, but it's also very satisfactory to see them in reality. So when we are considering, so we're using here benchmarking data sets. So these are the Europe data sets, and we're using them as if they are running, so they're captured at the same scene, but we're playing them back at the same time, considering that they're coming from different agents. Now, when we're considering these sequences independently, right, as if these two agents have been running independently, then this is the type of root mean square error that we get. But if we consider them together in this system that I mentioned before, where we have a central agent that is acting as this bookkeeping entity to merge paths when a place recognition instance happens, then we have a much lower RMSE error, which is expected when you're thinking about bundle adjustment, right? So bundle adjustment is exactly what it does. It takes all information and comes up with the best SLAM estimate that there could be. But the key difference here is that we're doing this at runtime. So with multi-agent collaboration, we can actually improve the accuracy not only after the mission, but also during the mission. So that has an effect into how good your estimates are at runtime. And of course, that means that it can have a much better effect on autonomous navigation at runtime. So what's next? Well, of course, you guessed it, centralized is our big bottleneck. So all data needs to pass through the server. We have some work that is looking towards removing redundant data. But of course, we work also towards distributed collaboration, which is a whole interesting story. Of course, in a way, centralized communication is helping us to use this centralized server. So for the moment, we're using Wi-Fi to communicate between our drones. I haven't really figured a way out to communicate with drones directly peer-to-peer, but we're working on the system that would be able, if we did have that technology easily accessible right now. And we're working also towards enabling stronger collaboration. So Marco just presented at ICRA, last ICRA, a method that can actually adjust the baseline of two drones holding one camera each, depending on the depth of the scene, creating this variable baseline stereo. Which is very, very helpful when you're doing high altitude flights. Right, so I talked about these three challenges because these are our drive to teach robots to see and collaborate in order to boost and advance robotic autonomy. And I did spend most of the talk mentioning works and showing you works about drones, but I wanted to show you also that the extension to other platforms can be straightforward. And here are some examples of past and ongoing projects that use similar ideas on automating train navigation or multiplayer phone gaming. And this is the last video that I wanted to show you, which I think it's also just to give a closure on advancing robotic vision and perception. So here we have, it's a collaborative effort with different labs at ETH. We use locally sourced zones and an autonomous excavator that is scanning for these stones and segmenting them out of their scene, figuring out how to grasp them, and using a background physics simulator to also figure out how to place them in order to create a stable wall out of them. And you're going to see the wall that was built within a course of few days. It's not the most beautiful wall that you've ever seen, but it's a wall built by an autonomous excavator, and each piece here weighs about a ton, which I think is pretty amazing. Yes, and with this, I would like to, well, of course, this is the team, it's not just me. Thank you for your attention, and I would like to take any questions.
Thanks, Margarita, for the very interesting talk. There is, we can start from YouTube stream, where I see one question from Mandela Wapo, why not use model predictive control instead of reinforcement learning?
Good question. Well, it's not one or the other, right? But I think that with reinforcement learning, deep reinforcement learning, we are still scratching the surface with what it is that we can do. And although I'm not a fan of replicating what happens in nature, I do use it as an inspiration, and I think it's much closer to how we are operating. So let's say that it's much more intuitive to me on figuring out how to formulate that reward, for example. And I'm not saying it's perfect, right? But yeah, we do need some of this intuition to see how far we can go with reinforcement learning. And who knows, maybe that's the answer, maybe it's not. And that's why we're all, there's a lot of myth there that happens in the research community.
Any more questions from someone here? I have one until someone else jumps in. So obviously, given your background and you did a lot of work on very efficient methods, right? So which I guess is comes from the stuff you have to deal with, which are drones and things like that. Are there any unique challenges when you, obviously there are, I mean, but what are the best way to describe the unique challenges that exist when you want to do, let's say, multi-user drone experiences in terms of computation or any other related issues?
Yeah, I think maybe, that's now the difference of the robotics community with respect to the vision community, right? And we have extremes in both cases, but also all the different variants in the middle, where on one side you have the class that says, I'm trying to create a reconstruction that looks as photorealistic as possible, and I don't really care if it corresponds to reality. And on the other side, you say, I want something that gives me an estimate as soon as possible because my drone is about to crash and I don't care if I carve that window in the best way possible. And I think with the advancement of time, we're working towards going towards similar direction, right? Because we want both. We want to be efficient and also be of high quality. But my experience with robotics is that ensuring robustness, although it sounds uncool, super uncool, I think it's the biggest source of impact, right? And this limitation that you might have in terms of resources or how dynamic or non-dynamic your platform is, it's all this decision making that, in a way, yes, it's driving us towards application-specific research, which again, it sounds uncool, but on the other hand, it is what we need to enable repeatable performance. And yeah, it depends who you're talking to, right? When you're talking to industry, people are like, oh, you guys in academia, you're in your own world. Wait until we apply your algorithms on our problems. And once they work, once they don't. And on the other hand, yes, so there's a lot of decision making that needs to happen in the process. There's no specific thing that I can say, just minimize the number of features. But maybe one big challenge is that one needs to be super informed about new technologies, battery lifetime, sensor technology, and a new drone, a new dumping system for your drone, all these things that you're relying also on other research areas to bring the solution to you such that you can use your perfect vision algorithm.
Okay, thanks a lot. Any other questions?
I have one
yes,
question. Regarding actually the semantic aware active perception on the bird's eye views, did you analyze on what kind of semantics? I think you mentioned like roads and trees. So I guess semantic segmentation. Yeah. Did you also look at like like different classes and how coarse it has to be, or maybe even
So we trained with 5 different classes, but I would like to think that there's nothing in the algorithm that really constrains the work into 5 classes. But we definitely have seen that it makes a difference with respect to the binary classification that is very often used, you know, of safe versus unsafe. But I don't know, again, thinking about how we do it, right? Usually water is a bad source of visual features. How about roads? Roads are sometimes good for visual features if they're empty, but pretty bad if there's traffic. So I think there's maybe that's where we can go with the semantics to figure out how much you contrast something. I'm not a fan of end-to-end learning without, let's say, some active intervention in the architecture of the decision making. But yeah, so I think that there's still a lot to, so I think we're just scratching the surface basically of what's happening there. And again, I think semantics can really change how we have been doing path planning so far. It is a very hard problem though to put all of these systems in a row and have it running on a real platform. You know, in simulation, you can freeze a SLAM and say, you know, I have a perfectly working SLAM, and let's look at how bad semantics can be or how bad my path planning can be now. If you put all the uncertainties in the pipeline for real experiments, yeah, we are, it's killing us for the moment. Yes.
Thanks.
Thank you.
Okay, thanks a lot. Yeah, thanks again, Margarita, for the great talk.
Thank you very much.
Thank you. Thanks. And yeah, we're moving on to the second invited talk for today, which is from Johanna Wald from TUM. And yeah, let's welcome Johanna, and looking forward to your talk.
Can you see my screen?
Yep.
Wait, sorry. So you see my screen.
Yes.
All right.
Yep.
Thanks for the great talk. Actually, I really enjoyed it, Margarita. I'm Johanna. I'm a senior PhD student at TUM, and actually a few days ago, I started a full-time role at X, which is formerly known as Google X. My talk is titled Relocalization Meets Scene Understanding, and I'm going to discuss why I think relocalization in changing environments is more relevant to scene understanding than it's actually currently treated, and particularly in these long-term setups. But let's first start with a very high-level definition of both of these areas. While camera relocalization is without a doubt pretty well defined, 3D scene understanding could mean a lot of different things. It's often associated with semantics, as we've just seen, or just the detection of objects, the analysis of like scene structure, layout, relationships between objects, and so on. The research community around both of these areas is pretty extensive. There's lots of workshops and papers are being published at every vision conference, probably also robotics conferences. While initially the focus was like a few years ago still on static scenes, this has slowly changed in the recent years towards dynamics, in particular for relocalization, as you can see with this workshop. This is also where I actually start my talk. I will come back to 3D scene understanding later, so just bear with me. 12 scenes and 7 scenes have long been the standard benchmarks for camera relocalization. Both of these datasets capture room-level scenes, and they assume the environment to be static. So that means objects stay pretty much at the fixed location, and the lighting is pretty consistent. So there are no changes. One of the first relocalization datasets that feature changes was the Aachen day-night dataset and the RoboCar seasons. It was also featured in this workshop, so that's exciting to see this research being pushed forward. Given the importance of relocalization, especially in these outdoor scenes for autonomous driving and so on, the community quickly picked up. More and more research is being done and has been released since then. It's, however, an outdoor setup. in terms of indoor relocalization, the pool is way smaller. InLoc was one of the first ones that was being published, followed by Rio 10 and the Gangnam Station, the Hyundai department store, and ETH Microsoft, all data sets that we see here in the workshop. I will focus on Rio 10 and describe that in a bit more detail, while the others focus on large-scale localization and public spaces, such as universities, train station, and shopping malls, which is pretty important to get be able to handle changes there. Rio is more like a private setup in bedrooms and apartments and so on. While I think these public spaces way more often feature humans, so the amount of change is different in diversity and so on. So that's why I think they are quite different. Rio 10 is the only one that is set up, as I said earlier, in everyday indoor environments, such as bedrooms and apartments and so on. And that's also what makes it unique. The sequences were recorded sometimes just a few days apart, but sometimes like several months. This includes, so they cover like changes such as different lighting and like here you can, for example, see there's this pink hue in the room. So someone was closing blinds that made the room look very different. Obviously, if you close, if it's not dark and you just turn on your nightstand light, then it will also have a very different appearance. The scene on the right looks quite static just from the first impression. So just have a quicker, a better look at it. The context and some of the objects have changed. Some objects disappeared, others got added. The more of these objects occupy the current view, the harder it actually gets to localize. So there's another example with a chair here. Overall, the dataset includes 10 diverse scenes with 5 to 12 rescans each. There's a total of 250,000 RGBD frames of 64 sequences. So the frames are grouped into 64 sequences, and all of them are coming with a corresponding 3D reconstruction. So when working on Rio 10, our goal was to understand the limitation and challenges of state-of-the-art camera relocalization, particularly in this kind of changing indoor environments. This requires two things, ways to measure change and ways to evaluate predictions. Obviously, people have evaluated camera relocalization before. I will just introduce an alternative measure, which I believe has many advantages. But let's first start with measuring scene change. Obviously, it all starts with some scene that was observed at some time, let's say T0. We want to compute or compare it to a scan that was recorded later. Here, for example, TS. The changes here are ironing boards. This is, I think, a laundry room. Ironing boards have moved, and like some baskets have also appeared in different locations. We also have the semantics of the scene, but let's start with the textured 3D reconstruction first. We propose to first compute visual change. It's computed with respect to a given camera pose, since it makes a big difference if you observe a static or a dynamic area of the room. PI here is the camera pose of the rescan. We'll render both scenes using the same camera pose, and then compute the 2D difference of these two renderings just by using a normalized correlation coefficient or the sum of the squared differences. The visual change is pretty high if the lighting or the texture or color of an object changes. It's, however, not capturing very well the geometric change. So if there's a door blocking the camera view and the background is white and the door is white, it will not be captured well with this measure. We therefore introduce a separate measure to account for geometric changes. It's, however, computed in a very similar way. It all starts just instead of rendering the color images, we render a depth map. We then compare pixel by pixel to, in the end, get an average depth difference in millimeters. Now, finally, coming back to the instance segmentation, we do the same for semantic change. It all starts again with camera poses, and like using this in the rendering function, we obtain 2D semantic masks given the camera poses. And the semantic change then measures the amount of pixels that have just changed in instances. Here we highlight it in black. This way we capture scene change using visual, geometric, and semantic change. This allows to categorize test images into different levels of difficulty, and therefore help us analyze how well state-of-the-art algorithms handle this kind of changes. As a side note, the last two, so the semantic and the geometric change, require ground truth in form of 3D geometry and semantics. So it could be applied to any data set that provides these, but also is limited, obviously. If you don't have this kind of data annotation, you cannot use these measures. The next topic I would like to discuss is how camera relocalization could be measured. A small fact just to throw in here, I've seen people discuss, I think Torsten even, with a paper on pseudo ground truth poses in Rio 10, or not just pseudo ground truth poses in general. In Rio 10, they are actually computed using bundle adjustment algorithms on features for fisheye images. So there's an additional sensor that has a wider field of view, which obviously is not perfect, but it's a good way to get a reliable ground truth, I think. So the fisheye images have not been released, but the pictures that you see in the background, this is images that we released. All right, so given a predicted and a ground truth pose, the performance is then measured. In general, like this is a very common way, just using the absolute pose error. For this, there's a translation error, there's an orientation error, they're computed independently. Then there's two thresholds, often for indoor scenes is 5 centimeters and 5 degrees. They are used to compute a recall metric. The absolute pose error has the disadvantage that it doesn't really correlate with the visual appearance of a scene. So, for example, in the setup where I'm right now in my office, a translation error of 50 centimeters is pretty drastic, while if you're on a drone and you're 50 centimeters off, it's actually less relevant. I think it's pretty accurate. Furthermore, these two values are interdependent, so rotation and translation could even slightly correct one another. We propose to use the reprojection error instead. It's a metric that's based on the 3D model of the scene, could also be a sparse 3D map. We then aim to obtain ground truth correspondences between the 3D points, so 3D rendered back to 2D, in the predicted view and respect to the ground truth. 3D point cloud is generated by back projecting the depth given the ground truth pose and the intrinsics of the camera. And then based on the predicted camera pose, the dense correspondences can then be obtained. So you basically know exactly how much the points have traveled or how off your image is. This is a simple pixel offset, so a reprojection error, just with ground truth correspondences. We then compute the average reprojection error, so the average of the length of these little vectors that I've shown before, and normalize it also by the image diagonal to account for different image resolutions. Like here, I've downsampled the images just for visualization purposes. The images on the left here have a very, very low reprojection error. Also, the rotation and translation is very low, as you can see. The predictions in the third and fourth column are around 10% off, while everything to the right is quite wrong. The measure has the advantage that it's just a single value. So you also would just need one single threshold. The dense correspondence reprojection error, or we call it DCRE short, can also be used to measure pose similarity. So if you have two different trajectories, like a train trajectory and an image in a test scene, you could find a nearest neighbor of a test image, which is what we did here, even though they were recorded different times. And you can see like there's a basket that appeared here, for example. Even though these look from the first view very different, this is approximately the same pose. And I think we all can argue that this is a pretty hard example to localize. All right, and so like using this ways to measure change and this metric to measure performance, we tested how well methods actually could correctly localize on the data set. And in initial experiments, we found that less than 50% of the frames were correctly localized by state-of-the-art methods. And the performance drops even further the more change is present in an image. So there's spoiler alert, we got some significant improvements by the challenge participants, and I'm pretty excited to listen to the talk later to see how they actually did it and how they made it work. One of the challenges when localizing in these indoor scenes are the large semantic changes, such as moving objects and furniture. And such situations, the method potentially relocalize with respect to the object that's dominating the view, rather than with respect to the scene. As a reminder, the only available scene during training is the one on the right, so this one. Given the reference view, so this one, it's pretty much impossible to find out where this image was taken or do it right, because if the map is not up to date and the background is not giving you any hints, you would probably localize something like this, which is pretty off. All right, so the next question is, can we detect these kind of changes to update the map as it's our source of truth? This will turn the localization into an iterative process, pretty much into some sort of persistent slam. This brings me to the second part of my talk, which is on 3D scene understanding. There are countless methods for 3D semantic segmentation, for instance segmentation, and so on. For object detection, semantics is pretty useful, as we've also seen in the talk before, for understanding statics and dynamics. Some papers already use it. We have just seen one, also for like long-term visual localization. I'm sure most of you are aware of some of them, so I will skip like just the topic semantics and instances, and instead talk about long-term association and scene graphs as they describe object relationships, something that is often left out. Let's first start talking about RIO, which is also called FreeRScan. It's the underlying data set of the Rio 10 benchmark, which I had previously described. It was initially published for a very different task, object instance relocalization, and it consists of static snapshots of an indoor environment. So it does not feature dynamics such as watching someone dance or someone throw a ball or something like that. But it has some low dynamics. So when something has changed after being reobserved at a later point in time. These long-term changes are interesting for a long list of applications. Let's say you have a household robot that comes back to a place after it's been offline, after the battery was down. Or for example, you have an augmented reality user that adds and interacts with virtual content and added something to the living room scene, for example, in a gaming setup. The dataset offers not only 3D models and semantic annotations, but it also has transformations of rigid objects, as you see here. So Rio is pretty big. It's almost 1,500 scans of 478 scenes with 2D sequences and 3D models, as I just mentioned. It has dense instance annotations, which also serve as a basis for the change computation that I talked about earlier. That's the one that I distinguished between visual, geometric, and semantic change. Just for reference, in Rio 10, we used only 10 of these 478 scenes, therefore also the name Rio 10. We chose a subset for the camera relocalization evaluation, just to make it easier to evaluate and more scalable also for future research. The selected sequences are, however, quite representative, and they're also very diverse in terms of their changes. But Rio also offers way more for learning potential priors and so on. It has different types of environments, and it's basically suited for data-hungry, long-term scene understanding tasks. One of it being relocalization or reassociation of objects. Where given the objects in a scene here, you see it on the left, we want to estimate the corresponding 6 degree of freedom transformation into another scan of the same environment taken at a later point. To automatically find these transformations is actually quite challenging due to partial observation and the changes in the surrounding context. Also, there's a visual change that can happen, like colors in the scene could appear very differently and under different light. Back then, we released a data-driven approach for this type of localization that learns correspondences and features that are change invariant. The network is fully convolutional, and it's designed as a triplet architecture. It operates on multiple scales, and it learns a feature representation locally that is persistent even if the context around an object is changed, and it does that by being trained with this kind of data. And it basically is trained with patches on objects that move around. The transformations are then obtained by combining these features with just some classical post-optimization. So in summary, there is a Rio data set, the instance relocalization task for map updates, as well as the learning correspondence network. If you're interested in any of these topics, feel free to have a look at their respective paper. Also, there's a work from my colleagues at TUM that have presented this week about scene generation and manipulation using scene graphs. They also provide canonical poses for the Rio data set, in case that's useful to anyone. So this leads me to this semantics, or the semantic scene graphs for Rio, which we published at last year's CVPR. Scene graphs organize the entities of a scene into a graph structure where objects are the graph nodes and the relationships are modeled as semantic edges. This is a 3D counterpart of the popular 2D semantic scene graphs introduced by Johnson et al. I personally believe scene graphs are a great representation, the holy grail of 3D scene understanding, and paired with the underlying data source of changes and rescans, I believe it enables a long list of new applications, from semantic change detection to visual questioning and answering and so on. But first, let's start with the basics again, and let's describe what kind of graphs I'm actually exactly talking about, because there's a lot of confusion and different definitions of what a scene graph is. For the semantic scene graphs that I'm talking about, the scene graph itself is very closely related to instance segmentation, where each object instance is a node in the graph. So here, for example, the 2 black chairs, as well as the floor, they are all a node, and they are described by semantic labels, for example, chair or floor. The connection between those nodes are also of semantic nature. And we refer to, sorry, so it's too far. We refer to the connected nodes, so 2 nodes and an edge in between, as a tuple, as a triple. The objects and the subject, as well as the predicate that connects those two. The nodes are further described by properties, for example, about the material or the texture of an object, or the size and the shape, which is just additional information that describes the object. To learn such a semantic scene graph means to predict the semantics of the nodes and the edges given a 3D model, which is what we did with the point-based architecture and a graph neural network that was able to predict node and edge labels. The method operated offline, or operates offline, and expects the scene to be pre-processed and pre-recorded, obviously. Instead of using a small set of semantic classes, the network is trained with a large variety of more than 160 classes. It's trained with guitars and stools, boxes, garbage bins and chairs, and so on. Feel free to check out also this paper if you're interested in any of the details. Another work that I quickly want to mention is a follow-up paper where we incrementally predict semantic scene graphs, besides a panoptic and a semantic instance segmentation, all done in real time. The method is pretty efficient as it operates on the geometric segmentation of the scene. So a segment is a node in the graph. And we also use so-called part-of relationships that help combine segments into entities and instances. One of the main contributions of the paper is also a novel attention mechanism that is well suited for this incremental procedure. All right, so when we released the graph dataset, we also wanted to prove the usefulness of scene graphs in an application. And we did this by incorporating them into a cross-domain retrieval task, which we call 2D 3D scene retrieval. So given a database of 3D scans and an input image, or a list of input images, the task is to find the 3D scene this image was taken. So I'm scanning it, or like over all the scans in the database, and I want to find the match. There's not only domain gap in terms of the data representation, but also one in terms of the scene change. So you can see here the chairs, they have a different location. Maybe there's different objects appearing on the table and so on. This setup is pretty challenging, and it usually requires to lift the 3D scenes to 2D by rendering them, or to lift the 2D images to 3D, or to finally design some sort of common feature space for both of these domains. In our experiments, we decided to use graphs as the shared representation. The matching then happens in the graph domain itself via some approximation to keep the efficiency high. Graphs are extracted for the 2D images by rendering them. Rendering a graph means to filter nodes and edges that are outside of the first one. While this experiment was more of a small proof of concept rather than an extensive evaluation, it shows the applicability of scene graphs in relocalization, especially when the domains are different and also very challenging. This could include point clouds or natural language. So for example, when I tell you I'm looking for a scene where there's 2 armchairs that look the same, both are next to a TV and there's some plant hanging on the ceiling, then maybe if you have seen such a room, you would know exactly what I'm talking about. So such an algorithm would obviously give us a rough semantic localization, but this shouldn't be confused with this very classical camera relocalization where we get a pose with 6 degrees of freedom. But it might be an efficient way, just have some initial rough estimate for further refinement. The graph matching itself actually compares nodes and edges of the graph. And when given 2 graphs of the same 3D scene, as you see here, the algorithm gives semantic change detection as a side product, which is easy to understand as a human and could even be like further parsed into a sentence or something like that. Here you can see, for example, there's a small bag that just disappeared on this couch, or this chair here, it moved closer to the bed, or the pillows, they were like spreaded and they're now piled together. So they are now close by, which is the relationship that was added in this setup. While scene understanding and relocalization are currently still mostly considered 2 distinctive research areas, I believe camera relocalization, especially in long-term incremental setups, could benefit from high-level knowledge, semantics, and so on, or even scene graphs. I actually, in summary, believe that we all agree that static camera relocalization is getting a bit boring and therefore more challenging benchmarks are required. So I'm pretty excited to see so many data sets at the workshop and people being interested in submitting. Furthermore, I personally believe that long-term camera relocalization requires high-level scene understanding, which ultimately goes beyond the static scene assumption, such as classifying a pre-recorded static scene. Then the analysis of these spatial temporal changes should be part of scene understanding as much as object detection or as much as pose estimation is. And then, or for example, a long-term object association, which I think is actually closely related to camera relocalization. It's the same task, just on a different level of detail. Instead of matching the full picture, you would just match the image against a known scene, the image of the object. Both tasks could even be solved with the same algorithm or with a similar algorithm. Finally, I think scene graphs, even beyond the ones that I presented, potentially including some low-level features, could be a very efficient hierarchical representation for localization, as they are efficient and human-readable. With this, I want to finish my talk. Thanks for everyone joining. I'm super thankful for the invitation and opportunity to give this talk. And finally, also thanks to all my collaborators. I couldn't have done that without them. Excited to take any questions now.
Thanks, Johanna. Thanks for a great talk. I have one until someone else wants to ask something. So at some point, obviously, you will reach a point, let's say if you're looking at very long-term changes, right? You will reach a point where it will be very difficult to distinguish if it's the same room or not. And you could also ask the question, I guess, but it's more difficult to answer. What makes it be the same room, right? So have you thought about this kind of question, the very long term? When do you stop considering this the same room or something like that?
Yeah, actually, I have thought about it, especially when people like moved out of an apartment and someone else moved in and stuff like that. I mean, I think it has to be at least recognizable by a human. That is just my, and obviously like we want to work on like realistic scenarios. So as I said, you have like a household robot or you have an augmented reality setup. In the worst case, you would just restart your scan. You would just restart from scratch, which obviously is something you don't want to do as like someone providing a product that should be reliable to these relocalization, long-term relocalizations or these changes. So I think as long as a human would be able to relocalize, this is something that an application should. And also like imagine the use case that you want to put something on a chair as like a virtual content and you want it to stick there, or you're a robot and you want to relocalize, maybe you want to be like have a virtual assistant that is able to understand what kind of objects belong to you and so on. So I think this relocalization of object is an interesting topic. And yeah, but if you move out of an apartment and someone else moves in, I personally would say that's a different scene.
Yeah, I guess that's a very extreme, way of thinking about this. So you're mostly, interested in the day-to-day changes, right? And understanding them.
Yeah, day to day or day to week. But it can actually even be that I drive to IKEA, I buy a bunch of new furniture and I put it in my apartment, and I don't want my household robot to be completely confused because I put new furniture there. Or if I'm moving things because I want to have a corner for my office, then it should still be able to operate and not have to scan everything from scratch.
Okay, thanks. Any more questions from the Zoom room? I think there's one from YouTube stream. Let me quickly pass it on. From the Nier, actually not a question. How do you do long-term localization in the SIP of Theseus? Okay, yeah, that's an interesting one, and I guess it will involve different things, right? And from Manuel, any thoughts, previous work about figuring out whether to ignore a change, considering transient versus including the change in the map? For example, considering a permanent change.
Yeah, actually, I think that's a really good question, because this is currently like just including the change or just keeping track of all the ways how a map could look like is something that I've seen a lot of different teams have. Like, this is something that I think is being used in industry already. Like, this is something that works apparently. For example, if I have my standing table, it has like certain locations. So sometimes it's up, sometimes it's down. It's kind of like a state. Or maybe even like a toilet seat, it's usually like up or down, or chairs are at my dining table. They're sometimes like close to the table, cleaned up, but sometimes they're out. So it has like some set of predefined states. And in this case, maybe it actually makes sense to just keep in like both. When to ignore changes, definitely if it's dynamics, obviously, like if there's humans walking around, you should just ignore that, except if you want to track them. But yeah, I personally think for furniture, it's interesting because if you know there's a chair, then maybe you want to keep track of it and have a 3D reconstruction of the or objects in general that I've shown. I think it's interesting to compute these changes for something that's moving and more dynamic like humans, then maybe ignore, except if you want to track them.
Okay, great. Thanks again, Johanna, for the great talk. I think there are no more questions. And with that, we're going to have a short coffee break, 15 minutes, and then we'll be back. Okay, I think the coffee time is up. So we're back from the break. And we're now moving on to the next part of the workshop, which is the talks of the talent winners. We start with challenges 1 or 2, which, as we said before, they have the same winners. And we first start from the Meglog team, from Sushi Peng and the rest of the team from, as I said, they developed the Meglog method. Unfortunately, it's quite late with respect to time zones where the speakers are, so they send a pre-recorded video, which we will watch now.
Welcome everyone. We are participants from MacRead 3D. We are honored to win the first place in the ICCV 2021 Long-Term Visual Localization Challenge. We now are happy to introduce you our approach. This is an overview of our pipeline. To be more specific, our pipeline is basically divided into 2 parts, namely mapping and localizing. In mapping stage, we have mainly 3 steps. Firstly, we extract local features of reference image using CNN. After that, we obtain the corresponding dense using superglue, the state-of-the-art matching algorithm. We then triangulate these matches to reconstruct an initial 3D model. The initial 3D model is caused because of unexpected noises, so it's all to be refined. We thus refine the 3D model using depth verification and uncertainty rejection to obtain a more accurate 3D model. In localizing stage, we follow the procedures as follows. We first retrieve reference image, resemble most current query image using an implementation of global descriptor fusion. After obtain TORC-K retrieve reference image, we do local matches and PNP ransack to solve an initial camera pose. Finally, we adopt pose rerank and final optimization to refine camera pose and get a final pose. For local features, we adopt local features fusion of superpoint and ASL fit, and we match the features by superglue. In our experiments, we found that mapping and localization both suffer from frequent dynamic objects. So we use SpeedLab v3+ pre-trained on city-based dataset to mask this object. The dynamic classes include car, bikes, pedestrian, and so on. For image retrieval, we found that localization performance is hindered by the retrieval result. So we adopt a global descriptor fusion approach to obtain better retrieval results to improve the localizing result. The global descriptors include NetRelate, DELG, APGN, and OpenIDL.
So here we start the introduction of our mapping and localization pipeline. Triangulation was performed after matching, but the baseline in the XY direction of the camera coordinate system is often narrow, which causes the triangulated 3D map points suffering from a large uncertainty. We can use steps or uncertainty to solve this problem. So the first option is to do the correction by depth scan. In some datasets, certain pixels of the images have a very accurate depth, such as Gangnam Station and Hyundai. We built a point cloud map by depth, which can be used to correct points and move outliers. As you can see from the example here, after remove those points with an incorrect depth, we can obtain a cleaner map. So the second option to refine the reconstructed map is to correct by uncertainty. So the uncertainty can be retrieved by the projection Jacobian, and we can accumulate the uncertainty of one point by its different observations. So here is an example of using uncertainty to correct the preliminary 3D map. As you can see, at the beginning, the map is very noisy, and after thresholding the uncertainty, we can get a more clean and accurate 3D map. All right, so here comes the localization part. So first of all, we need to cluster all the images according to their co-visibility and the pose. The motivation of doing so is that we observe the fact that for a given query image, its corresponding database images may distribute diversely over the whole 3D space, which makes the conventional PMP and RANSAC difficult to handle. So database images are clustered by their co-visibility relationship or their 3D poses, and query images poses are estimated for each cluster. All estimate poses will get a rank and based on a certain criteria, which will be illustrated later. So only those database images related to the top one pose are kept for the final pose refinement. So here is one of the strategies we use for pose re-rank is to use rendering. So here is a very common case in indoor scenes where we always suffer from duplicate texture information and objects. So here are the two retrieved images of this given query image. As you can see, the top one image is not correct. So we use the estimated camera pose and the given depth map to render those two poses, and we can have an alignment with the original given query image. So we can compare this rendered image to the query image according to the perceptual similarity. So as you can see, with this perceptual similarity, we can see that the second image, which was originally the top two image, is better than the original first top one image. So here is another trick we use at the localization stage is that we localize image poses with more 2D features. So compared to localization with only few reconstructed 3D points in the common method, we triangulate new 3D points according to matches of local feature from query and database images after initial pose from PMP and RANSAC. Finally, bundle adjustment is performed while fixing the poses of the database images. In this way, we can utilize more observations and thus add more constraints to the camera poses optimization. In some extreme cases that have no reconstructed 3D points in query image, we can still solve correct pose using this method. And as a result, the precision of the localization has been improved using this strategy. Okay, so uncertainty can also be utilized at this stage of final optimization. So since we can get the uncertainty or covariance of each point, and we can project it onto the image coordinate system using camera intrinsics and extrinsics, and we can redefine the reprojection error with the uncertainty. And now we use uncertainty error as the optimization objective of the final optimization. So there's another strategy we can use to refine our final camera pose is that For cases that the query depth is given, such as real 10 in this workshop, we can use ICP to refine the camera poses. As you can see from the blue frame, that it is the rendered depth by the first preliminary estimated camera pose, and we have a query depth which should be the target of the optimization. We can use ICP to do this refinement. As you can see in the purple frame, that the refined depth is quite similar to the query depth. So as a result, the camera pose is optimized too. So here you can see the results of using this strategy.
Okay, finally, there are some our attempts, but not fully implemented yet because of our limited time and resource. And first, for some indoor data sets like eLog, there are some line structure in the scene. So we can extract the line features and using line matching with the descriptors. And in this way, we can utilize more geometric characters, and we have relevant work which is called a line detector, and the descriptors is published in ICCV 2021. And second, we can use dense mapping and post refinement. First, we can get the 3D mesh model by using MVS with a surface reconstruction or using NERF. And given the 3D model, we can render the image by initial cross pose, and then using differential for rendering, we can refine the pose. Finally, we can get the final image with is much similar with the query image. And using this, we can get using more texture information, and which is more useful than the sparse 3D model. Finally, the overview of our results in the different data sets. And thank you for listening. If you have any questions, please feel free to send us its message.
Okay, so that was a talk from the MEGV team, the winners of challenges 1 and 2. And moving on, we're going to the runner-up of challenges 1 and 2, O-Space from Gao and et al. And again, once again, this is a pre-recorded talk. So yeah, I hope you enjoy it.
Hello everyone, my name is Shuang Gao. I'm an engineer from Oppo Research Institute. Today it's my pleasure to introduce our visual localization with RLOGs and point line optimization, which has won the second place in ICCV 2021 challenge of long-term visual localization under change conditions, in-DAO and out-DAO visual localization challenge. I'm very thankful to my collaborators Xu Dongzhang, Yu Chenyang, Yi Shanping, Ji Xiangwan, Kun Jiang, Xiaohu Nan, Yu Lin Sun, Ji Junan Li, and Yan Dongguo. This is the overall pipeline of our approach. It includes two parts. The first is RLOGs, which was introduced in Acra 2021. RLOGs is a general mapping and localization system. It can rebuild sparse point cloud map from database images. Also, it can localize the query image by image retriever, deep learning features, and PNP runsec. The second one is specific optimization method according to the different characteristics of datasets. Retrieval constraint works on robot car, gun station, having that department store. Database extension works on real-time. Multi-camera optimization works on robot cars, pseudo, ETH regions. Secondary localization works on ETH regions. And the point line optimization works on icon and in-lock. The general pipeline contains two parts, mapping and localization. In mapping stage, we use global filter APGM to achieve image retrieval. The local filter is the point, and the matching method is glue. And we use COMAP to triangulate a sparse point cloud model. In localization stage, we extract the same local filter point of query image. An actual double image retriever is utilized to get similar database images. Then we use the subglue to match local features between query and top case similar database images. In 3D2D matches filtering, we firstly use PNP ransack between the query and each candidate images to filter the outlines. Moreover, we filter the 3D with large arrow and short track length. After that, all matches are merged and do another PNP ransack to get the final camera poses. The general pipeline works for almost all databases in this challenge. Next, I will detail some optimization methods for different datasets. The first is retrieval constraint. For the robot car, there are three different views with the same timestamp in both query and database. Firstly, we do the image retrieval for each view respectively. If three candidate images have the same timestamp, they are high quality retrieval and will be reserved. If two of the three candidate images have the same timestamp, they are middle quality retrieval and will be extended and reserved. If all three candidates have different timestamps, they are low quality retrieval and will be failed. Another type of retrieval constraint can also be called sequential constraint. For gun station and having that department store datasets, there are lots of similar scenarios in database map. However, their query images are serialized. We can use the localization result of the last frame to constrain the retrieval range of the current frame. It can avoid the similar but distant database as candidate images, so that we can improve the retrieval accuracy and get a more accurate pose. The second method is called database extension. For real dataset, query images are similar enough to each other. Some can localize successfully, but some cannot. This part uses well-localized cameras to help localizing poor localized cameras. It can also be called query to query. But how to judge whether the query image is well localized or not? Here, we use Monte Carlo simply to sample half matches and do a PNP ransack to get a subpose. If a query image's localization result is correct, the matches should be regular. Then, sample matches should also be regular and produce the similar camera pose results. So, we compared distance between camera pose from outlogs. And if the distance is too large, this camera pose shouldn't be very accurate. We use accurate camera depth map to localize the failed cases. Finally, some of the failed cases in outlogs can be solved. The third method is multi-camera optimization. In this challenge, there are three datasets are rigid cameras, robot car, pseudo, and ETH. Firstly, we extrude single frame localization to get the initial camera poses and 2D, 3D inline matches. Secondly, we transform camera poses to the best localized camera coordinate by rigid transform matrix. Then we reproject the 3D point to the current pose and filter them with large projectile arrow. Finally, we minimized the resolved reprojection error using CD solver. In this case, the green line segment represents the line between the 3D project point and the corresponding 2D point. We can see that the third image has large reproject errors. Its matches will be filled. The fourth method is secondary localization. It works on ETH rigid cameras. There are similar scenarios in ETH datasets, and 4 cameras might be localized in different positions. After the first localization, we will class the 4 poses. If the class size is 1, means the 4 camera poses are close enough, and we will believe the results. If the class size is not 1, for each class, we do retrieval constraint by the center of class and localize them again. Then choose a class with the most elements as the final results. For example, after first localization, there are 2 classes, means 2 potential poles of the rigid cameras. Then retrieval range is constrained by the center of class and do central localization. We found that both result has 1 class, and we chose the one with the most inline matches. The last method is point line optimization. This work is submitted to the ACRA 2022. The paper named Pose Refinement with Joint Optimization of Visual Points and Lines proposes a camera pose optimization method using point and line features. The pipeline of our method contains 4 modules. Module 1 is line extract. Module 2 is 3D line map reconstruction. Module 3 is line matching and filtering. Module 4 is point line joint optimization. In the line extract module, we propose a more accurate visual line detection CN named VLSE. In the line matching module, we designed a cost-to-find line matching method based on initial pose, which takes advantage of geometric constraints and the project filtering to the select high-quality line matches. In the 3D line map reconstruction module, we use different methods according to the different characteristics of datasets. For icon, we use COMAP and line 3D PP. For inlock, we use depth mapping. In the final module, we designed a point line joint cost function to get the final pose. On the right, we can see that map the 3D line reproject on the query images, and the error is small. Finally, let's make a summary and outlook. The advantage of our method is that we use simple localization pipeline. Our pipeline is similar with open source approaches such as HLOC and capture, but not exactly the same. Also, different optimization methods are adopted according to the different characteristics of datasets, such as retrieval constraint, database extension, multi-camera optimization, secondary localization, and point line optimization. The limitations of our method is that it's not very efficient and it can't run online. As for the future work, we firstly would like to solve the limitations. Also, we want to integrate some sensors such as GPS in outdoor environment and Wi-Fi in indoor environment. That's all. Thank you. Any question? feel free to contact me.
Okay, so that was also the second talk from the runners-up of challenges 1 or 2. And moving on, we're going to challenge 3 now, the place recognition challenge, where the winning team was a team from ZTZU and the rest of the MEGV team there. And unfortunately, once again, due to the time zone constraints, this is a pre-recorded talk, I believe the last one. So yes, let's also hear from these authors about the place recognition pipeline they put together.
Hi, everyone. We are the team from MEGVI Technology. We focus on the third track of the competition, place recognition. And below we will introduce our competition plan in detail. Our plan is a slight and effective pipeline. It is destined based on unsupervised local matching learning. For simplicity, we refer to it as MEGLOC ULM. As shown in the figure below, our MEGLOC ULM contains 5 main modules. The first 3 modules represents the training process, and the latter 2 modules describe the specific inference process. In the training process, we split and refine the optimization target. 3 training phases are performed successively. Such a strategy not only greatly shortens the training time, but also improves the discriminativeness of the network. In the testing process, we gradually eliminated hard negative samples in a way that is easy first and then difficult. 3 ranking phases are executed successively to get final ranking result. Next, we will introduce each module in detail. First of all, in the global training phase, we use the same network structure as PatchNetLad. We employ VGG16 as our backbone and optimize the parameters of the last block and the NetLad layer. Different from PatchNetLad, at this stage, we do not perform hard sample mining, but use random sampling to construct triplets. Because we believe that, in the one hand, in the early stage of training, the parameters are changed drastically and the model does not have the ability to really select difficult samples. In this case, relying on the previous model for triplet selection has the risk of getting more training bias. On the other hand, selecting samples too early will reduce the diversity of negative samples, which is not good for training. Secondly, to speed up training, we adopt a distributed strategy to distribute 440,000 training samples to different GPUs, which greatly improves the training speed. From the experimental results, our global training strategy has high time efficiency and its performance is comparable to PatchNetLad, which lays a solid foundation for our next optimization. After completing the global training, we design a local feature matching branch to further improve the expressiveness of the network. Our local branch consists of a lightweight transformer. Given a query and a candidate image, we first calculate local features and then predict the matching relationship between local features. The output of local branch is a probability matrix. Similar local features gets high probability. Considering that MSLS dataset does not provide local matching relationship, we use nearest neighbor and ransack to generate pseudo-labels, and the local branch is trained using this pseudo-similarity matrix. The comparative experiments shows that the introduction of our local matching branch can greatly improve of the discriminativeness of global features. On the validation set, our performance is already 3.4% higher than the original PatchNetLad, and we still have a great advantage in training time. Next, we execute hard sample mining. At this stage, the model has converged. In order to further mine more knowledge from the data and avoid accumulating errors, we adopt 2 difficult sample mining strategies, which is slightly different from PatchNetVLad. For hard negative sample mining, we're using a self-selection strategy. Just like PatchNetVLad, we select negative pairs with high similarity. For hard positive sample mining, we employ GCL annotation. We define the similarity of positive pairs using field of view values. The lower the value, the harder the pair. At this stage, the performance of ULM has increased by approximately 1.5%. After completing the training, we use the trained model for inference. During inference, we use global to local strategy to rank database images for each query. We first select the top 300 candidates based on the global feature similarity. The global matching is fast and provides reliable candidates. In this step, easy negative samples are filtered. Then, we refer to PatchNet VLAD and re-rank the candidates based on local feature similarity. The top 200 candidates are retained for subsequent fine re-ranking. Local feature matching optimizes the global ranking. It narrows the scope and further reduces the follow-up processing time. We achieve a score of 85.54 and rank one of the SF scene after local feature matching. Finally, we perform fine re-rank. In this process, we use two models, SuperPoint and SuperGLUE, where SuperGLUE is trained on the megadepth training set. We extract local features of those candidates obtained at previous stage using SuperPoint and perform matching with query using SuperGLUE to analyze their similarity relationship. In order to maximize its effect, we do a series of comparative experiments and choose the best configuration. That is, using 100 homography matrix transformations to get 100 transformed images. Extract key points from all of these images and then get a heat map of n key points. Add these n heat maps to get the final heat map for key point selection. In this way, we can obtain more useful and reasonable key points. After obtain match results of each candidate pair, we re-rank them using a ratio-based strategy. By calculating the matching ratio of key points, we calibrate the matching score of each pair. We also tried some integration strategy, but the effect on the test set was not obvious, so finally we chose SuperPoint. After effectively combining these modules, we finally achieved good results on the test set. The details are shown in the table below. The above is all our sharing content. Thank you all.
Okay, that was a talk from the winners of Challenge 3. And now I believe we have Maria with us. She's going to present
yes, I'm here.
The work that led them to second place in the Place Recognition Challenge. So yes, take it away, Maria.
I think you have to stop sharing your screen.
Yeah, 1 second. That's your work now.
Can you see it?
Yes, yeah.
And you can hear me? Okay, all is fine. Well, hello everybody. My name is Maria Leiva Ballina. I am a PhD student in the University of Groningen, and I am going to talk about the work that I did for this challenge, which is titled Generalized Contrastive Optimization of Siamese Networks for Place Recognition. Well, first of all, the work for this challenge has been based entirely in my paper that I wrote with my co-authors, titled, well, the same as this presentation, which is available if you follow this QR. And moreover, I released the test code and the extra data that I used in my GitHub repository, which is the link that you see in your screen. The idea for this work started from a very straightforward thing. If you take a look at the popular visual place recognition data sets like Pittsburgh or Tokyo or mapillary street level sequences, which was the one that was used for this challenge, you will see that all of them define ground truth by labeling pairs as similar or dissimilar. Using a threshold, generally, two images will be labeled as similar if they are taken 25 meters away or closer. So for instance, for the query image that we see here, this image here will be labeled as a positive because it's taken 5.6 meters away. And this makes sense visually because you can see that it is the same building there, more or less from the same perspective, and is coherent. The second image, that is taken 24.7 meters away from the first, is also a positive, even though visually it's not so similar as before. The building is still there, but the perspective is different. These trees are new. It's a bit more hard. And this third example here that was taken 25.2 meters away from the first image is labeled as a negative, even though it is visually a little bit more similar than the image that we saw before that was still a positive. If we see all the images together, we observe the contradiction quite clearly. But it's not completely wrong, isn't it? I mean, we can all agree that the second image is quite similar to the first. The last one is a bit less similar, but a bit quite similar too. And the second to last is a bit less similar than the other two, but there are still some commonalities. So the straightforward idea that I came to is that ground truth similarity, instead of being defined like y equal to 0 or 1, should be defined as a continuous value, taking all kinds of values between 0 and 1, and I denoted this value psi. With this idea, we can reformulate the contrastive loss function. We can generalize it so that it is not only defined for psi equal to 0 and psi equal to 1, but to all the values in between. And I am not going to go into much details because, well, of the time constraints mainly, there are details in the paper, but this has a very interesting effect in the gradient, which means that during training, we will push similar perceived images together proportionally to their annotated degree of similarity, and we will push them away proportionally to their degree of dissimilarity, or 1 minus psi. So this is all very nice, but in theory, but the problem is that the data sets do not have this kind of ground truths. So what we did is we reannotated them. Here I illustrate the idea of the 2D field of view overlap, which is what we use to reannotate mapillary street level sequences. For each image, we have a translation vector, which is the GPS, the 0 and T1 in this figure, and a compass angle, which is alpha in this figure. If we define a theta, a camera angle, and a radius, theta is 90 degrees and the radius is 50 meters for all my experiments, we can estimate a 2D field of view for all the images. And for pairs of images, we calculate their overlap, which will give us an approximation of the degree of similarity that they share visually. And we have two examples here. The first one is a pretty strong positive with around 75% of overlap. And the second one is a less strong positive with around 50% of overlap. As a very quick side note, we can use this technique also to relabel other datasets with other ground truth available, like TV Places, which has 6 degrees of freedom pose, or 7 Scenes that has 3D information. Now, we have the function that we want to optimize, and we have the data that we need. So it's time to define an architecture. We use a Siamese architecture that consists of a fully convolutional backbone with a simple gem pooling on top. As backbone, we use ResNet 152 and ResNext 10132x8v, ResNext, for the rest of this presentation. The descriptors that we have are of size 2048, which is relatively small, and we train for one epoch around 500,000 pairs, the number of queries of the data set, but ResNext converges much earlier, around half of the training. We only update the 2 last convolutional blocks, and we do not use any pair mining. We just use balanced batches. So we make sure that half of the batch is labeled with similarity with psi higher than 50%, and the other half is lower than 50%. That's it. Finally, as post-processing, we use PCA. We learn the principal components on the map set, and we use those to project both map and query, and we see that this has a boost in the performance. So here are the results. In this graph and table, I also compare with the baselines NetBlood and Patch NetBlood with the numbers taken from the respective publications. And we see that the models taken, trained, optimizing a generalized contrastive loss outperform these baselines, even though the training process is much simpler and the dimensionality is lower. If we use PCA on top, we see that there is a boost in performance and the gap with the baseline is even higher, even if we reduce the dimensionality by half, as is the case of ResNext. As another side note, I have to comment that this also generalizes very well to the Pittsburgh and Tokyo data sets. We have the results in the paper. So finally, as a last small experiment, we decided to combine the retrievals of our two best performing methods. So for instance, for this query image, our best method, which is ResNext with PCA, predicts this top 5. And the second best, which is ResNet with PCA, predicts this top 5. So we decided to combine them by taking first method, first image, second method, top 1, first method, top 2, and so on. So this would be the combined prediction. So here are all the results. We see that the combining of the method of the rankings helps a little bit in Recolat 5 and a little bit in Recolat 20. Recolat 1 stays the same, obviously, and Recolat 10 is a bit lower. So it helps, doesn't hurt, but it doesn't go very far. So as conclusions, we observed that the models trained by optimizing a generalized contrastive loss function achieve a state-of-the-art performance for visual text recognition, even though it is a very simple training without any pair mining and with relatively low dimensionality. And well, this presentation is very short, so I am leaving a lot of details out. So please feel free to check our paper preprint. You can scan this QR code and it will send you there. If you have questions and we have time for questions, I am open to them now, or you can send me an email. So thank you very much for your attention.
Thanks, Maria. I have a short question, if you don't mind. So how do you see something like this working in the case where you're going for challenge 1 or 2, for example, the more accurate camera pose versions instead of the place recognition ones?
Do you mean for camera relocalization?
Yes, but for the very accurate case.
We did a small experiment with 7 scenes, and we observed that this helps with respect with training with binary labels. So we have not focused a lot experimentally in that, but it does help. I mean, better retrieval, better localization. That's the insight that we have at the moment.
Okay, thanks. And there's a question from Manuel. It seems like training with your loss does well even without mining. Do you have an intuition about why this is happening?
Well, thank you, Manuel, for the question. Yeah, I do have an intuition about why this happens. One of the ideas of mining is, well, selecting challenging pairs, but not too much, but also reliable pairs that are labeled as similar and are actually visually similar. But if we define the ground truth with the 2D field of view overlap, they will always have some visual similarity. It is an approximation, of course. It's not going to tell you the 100% accurate truth, but it will not tell you lies. So you don't have to filter out by computing the descriptors, etc., because the ground truth is already much better than using only the thresholds.
Okay, thank you. I don't see any more questions. So yeah, thanks again for your great talk.
Thank you.
Congratulations for the second place in the challenge. Okay, moving on, we're going back to our invited talks. So yes, I want to thank the next 2 speakers because it's quite early in Australia where they're coincidentally both based. So yeah, I want to thank them for waking up early to be with us and present their talks. So the next talk is from Hondong Lee from Australian National University, and I'm looking forward to your talk, Hondong.
Thanks, Lestra, and thanks for inviting me. I'm speaking from Australia. It's really my great pleasure to present our work. And of course, also thank you for joining this session, workshop. Let me share my screen. and just see whether you do see my screen. Okay.
Yes, that works.
Okay. Excuse me. It's my honor to present our work titled Visual Localization for Autonomous Vehicle by leveraging off-the-shelf satellite image. I am from Australian National University. So this work, of course, is a joint work with my co-authors and collaborators, in particular, Yu Zhao, Liu, Xin, and Dylan. They are PhD students and postdoctors. So the problem setting, well, this is what I simply copy from the website of this workshop. So visual localization is the problem of accurate estimating the position and orientation of a camera given image relative to some pre-recorded word representation or word map by using image or video. It is an important task in many applications. In the context of autonomous driving, the visual localization basically means to determine the fixed-off location and orientation of your vehicle based on a vehicle-mounted camera. So the word map may take different forms. Can be a laser point or can be lines, as we just watched the video. Can be image, road furniture, traffic sign, or semantic landmarks. And depending on the different forms, of word map, there are multiple different methods developed. We all know 2D image retrieval based, which basically treated the problem as a place recognition, landmark recognition, which give us relatively coarser localization. Or you could run a 2D, 3D direct feature matching based approach. And of course, we shouldn't forget the visual odometry, SLAM, or continuous structural motion pipeline. In this presentation, I like to focus some of our recent work based on cross-view matching. I'll come to this explanation of what is cross-view matching shortly. But before that, let's quickly use a few slides to review what the existing method look like. So the task recap, just from image, can we localize the camera? Can we localize the vehicle? Okay, in the 2D image retrieval based approach, where you take an image or a video and you register that, you match that against a collection, a database of geotagged image. And often this is treated as a landmark recognition. You see a building or a key landmark, you recognize where you are roughly. We can do it better. I mean, other than just give you a retrieval result, we can refine that using direct pose regression. The most well-known work recently is Kendall's PoseNet, where you run a direct regressor using a convolution neural net, direct give you a camera position, which is kind of impressive. The second type of approach rely on feature matching. Feature detect both in 2D image and 3D map. And in essence, this task converts to a perspective endpoint problem in multi-view geometry. You register 2D point with 3D. Our group in the past few years also developed some branch and bound global optimal approach for doing this task without knowing explicit 2D, 3D feature matching. I won't talk about this, but if you're interested, point you to a paper we published now it's 4 years ago. Let's move to the main subject of today's presentation, cross-view matching based visual localization using off-the-shelf high-definition satellite image. It's a bit long, but I hope you get the main idea. The main idea is, well, this is just saying in this talk, I'm going to cover two part of work we worked. One is the visual localization cross view, the other is a small extension. So the task of cross view matching is giving you a ground level captured street view image, for example, the picture on the left, and give you a big satellite map of the city you are interested in. Can we find one-to-one correspondence, particularly to pinpoint where exactly this image, treasure image, is taken on this map? And the basic concept is not unfamiliar. This is very much similar to landmark recognition-based approach. You have two images, although they're different. One is ground level, the other satellite. Can you find matches? I mean, this building matches that. If you lock this match, you then know where your camera, where the image was taken. However, compare with both single view, single modality view problem, this task is facing a number of challenges. So the central question now is how to tell whether or not two vastly looking different across view image were actually taken from the very spot. Here I show you some example. The left is a ground panorama. The right are some candidate image. Even for human eyes, it's very difficult to tell which is which makes a pair. So the challenge comes from multiple different factors. For example, obviously the view angle are different. They are orthogonal. Satellite image taken from sky, a ground view image from ground, and looking horizontally, the other vertically. So the appearance different. Sometimes even the contents are different. When I say contents different, it's easy to imagine. You see from top, when you see a treetop, roof, but this often not seen by ground view images, cameras. There are significant domain gap, occlusion, already mentioned that, and modality difference, and even the time of capture are vastly different. It can be differ by months or even years. So how to address this long-term issue is the key. So there are many, there are not too many, but there are quite a few existing approach published recently, especially those based on deep neural net. The earliest one after the deep neural booming is the work by Vo and James Hears. So localizing oriented street view using overhead imagery published in ICCV 2016. So they built up two frameworks. These two frameworks looks quite simple, but they are the standard approach nowadays also used quite popularly. One is you stack both matched pair of ground view and satellite image together and train a neural network and directly predict whether or not they form a pair or whether or not you can regress a meaningful position. The other way approach is more like the standard metric linear. You design a Summise neural net and train a metric linear approach using contrastive loss or triplet loss, again for the same structure. This work lately being extended by multiple follow-up works. One of the prominent ones is so-called CVMNet, published 2018. CVM stands for cross-view matching. So on top of the previous design, what they have is a global feature aggregator. So they basically use NetVLAD, and the NetVLAD collect spatial agnostic features and measure whether or not they are from the same pair. Okay, so the next part of work is based on some of our recent publications built upon their work and published over the past 2 years at CVPI and in Europe, etc. So our idea is we still use the same deep metric learning as the backbone, as a baseline. However, instead of treating these two images uniformly and train a black box-like deep neural net to predict whether or not they are taken from the same location, we attempt to inject as much human knowledge about localization and orientation as possible. So in other words, instead of doing a black box solution, we attempt at a gray box design. By gray box design, we mean we incorporate or inject extra knowledge about how you localize yourself, how you orientate yourself as much as possible to the design. And try to teach neural network the basic concept relevant for localization. For example, when you, well, suppose you are a tourist into a new city, you feel lost, you're disoriented. So, but fortunately, you have a satellite map. How would you read a map? Of course, you can imagine in that situation, you first want to orientate yourself. You want to know where you are facing, which direction. And then you find a semantic corresponding point. Our design basically follow this human intuition or human knowledge. So we want to find semantically related deep feature correspondence. And the first step is clearly still to detect some meaningful, semantically meaningful features, although we don't strive for the symbolic labels of the features. They are just the features. And once we detect that, we try let the neural net figure out, of course, through end-to-end training, which feature representation are in fact related across these different cross-view images. And the next key concept previous design have oversighted is orientation. When you look at this satellite map, the first thing you want to do is find out true north. And similarly, when you're sitting on somewhere on the earth, you want to orientate yourself. So this orientation information is in fact very important. How can we teach a neural net such concept? Okay, the task is actually quite simple. If suppose we know your heading direction, suppose we know for now, and for satellite image, it's quite reasonable. We can assume true north direction. So if we color coded this heading direction orientation using this color map or orientation map, we can simply inject this orientation or elevation angle map together with the input. So this explicitly tell the neural net, pay attention to this. So to some extent, you can understand this orientation map as a kind of user inject attention. And this way, when the CNN track features, they know there's something different and zero back to in back propagation training, they figure out the orientation are actually very important for this task. And thirdly, rather than treat these two images as a pair of single viewpoint image, we must understand that they are actually taken from totally different orientation, and they follow different image projection equations. So we use some simple transformation, homography or polar transformation, and to explicitly unwrap the image so that they look visually more similar to each other. So this way we provide the neural net an intermediate semi-transformed image so that they can easily find the matches. For example, this is a satellite image where you see on the left side. This is ground view image. Of course, they do not have easy correspondence geometrically. By using, for example, our proposed polar transformation, and then these two images looks more similar in the sense of geometric configuration are similar. So the road corresponding to road, of course, there are distortions because in doing this transformation, we actually made some approximation. We don't know the height of the thing, and the transformation is a fixed transformation. Nevertheless, finding feature correspondence between these two images, I mean, the ground view image and the transformed satellite image become easier, especially after we apply orientation attention. Okay, the final step, which is also an important step, is we must admit, despite of this semi-geometric transformation, the feature map are still not that straightforward to find. We develop optimal mass transport layer or modular. This modular basically find one-to-one matchings between the two feature maps extracted by these two transformed image. And if you're familiar with Earth mover distance, this is essentially solve minimum Earth mover distance transformation. Eventually, you get a permutation matrix, which tells you which feature mapped to which feature in the other image. So the effect of this optimal transport can be illustrated by this simple example. Well, you should read the second row, and this is the feature activation map extracted on this satellite image. And before we apply optimal transport, the detected feature map on the ground view image after transformation look like this. And after this optimal mass transport, the feature map changed to this one, the middle one. And you can see geometrically they are more or much better aligned. So combine this everything. Of course, I forgot to mention in the beginning of I describing our approach, we said, suppose we know the heading direction. So what if the vehicle's heading orientation is not known? Well, this can be solved by a dynamic correlation modular. The idea is if your orientation is not known, when you compute that, your feature map seems to shift either left way or right way. In this case, so this road actually shift to left. If we can design a correlation modular that test over a possible range of orientation, then we can correlate these two images by shifting a small angle. And this way, we automatically determine the orientation. And this is the task of this dynamic correlation module or dynamic matching module. So combining everything, we get a pretty complex designed neural network built upon the original deep metric linear network. So you have a ground view image, you have a satellite image. After this semi-transformation, you extract features, and the correlation matching modular trying to align them in the orientation, in the rotation angle, and eventually you use the triplet loss to train this neural network end to end. Okay, this completes the description of our network. Let's come to some result. Let me check the time. Yeah, okay, good. So experiment. We tested on the standard CV USA data set. We also collect and create a large-scale open cross-view satellite image localization dataset we call CVACT dataset. And this dataset covers a big range of the entire city of Canberra, where I'm currently based on. So the size is over 30 kilometer by 30 kilometer. And compare with previous biggest dataset, our dataset contains 10 times more testing image pairs. We have all accurate GPS tags where the previous database didn't have, and image resolution also much higher. We maintain the training example, the number of training examples the same. So this is open, you can download from our website. So test on this, I show you first some visualization, some qualitative matching result. And the left column are different query images, ground view based. And the right one are the detected top 5. Of course, the color is green, this is the positive, and the red are some negative. But if you look at the result, they are visually very similar. And the correct one in these 4 cases all in the top 2 or top 1, if the top 1 is the correct matches. Remember, we also have this automatic orientation discovery module by dynamic matching. We can refine angles. Here are some quantitative results using recall read. And on CVUSA, our method achieved 92, 97, 98. And well, compare with previous method, they are big jump. The second, the last is also our method published a year earlier. So you can see the trend jump from 20% to 50, now to 90. I believe this is top 1. This is second column is top 5, and top 1% is already close to practical use. Our method is also able to determine the angle, the orientation, quite accurately. You know, the ground truth orientation is minus 32, our detected is 33. Oh, this is similar. Okay, so if the orientation estimation is not correct, we are able to correct that after this alignment, orientation alignment. Okay, I can skip this. So this is a real test example. I took this image myself, and this is in fact my building, my office, and the result precisely here. I mean, this is a real test example. Okay, I think I have 10 minutes. I will cover the second part, which, as I said, is a simple, small extension, but quite interesting applications, I would say. So satellite view to ground view, null view prediction, or null view synthesis, if you like. So the idea is kind of a reverse problem. Suppose you are given a satellite image nowhere, I mean, maybe a street, or you've never been there, and you have a position, you know your position. So you want to, given this image, you try to predict or synthesize a ground level street view image. So in other words, you wonder, what does it look like if I was down there and looking around? So in other words, this is the input and this is output. Can we do this? Well, magically, the neural net seems capable to either remember or interpolate this task. So just to repeat, the input are a patch of satellite image. And we, of course, train this neural network using examples. We want to design output is this thing. Of course, you can imagine if this is done perfectly, you can localize quite easily, but that's a different story. For now, we only interested, can we convert this image to something look like this? Again, we try to utilize or exploit the known geometry. So this is how the two images are captured. Satellite image taking picture from above and ground view image from sideways. And just imagine if we know the height of every scene point, we should be able to predict where this scene point project to. I mean, you probably see my mouth. So the idea is, if we are able to estimate height, then we should be able to convert this height map or multiple height map to a ground level based camera view and eventually get a ground view image. This is the idea. If you're familiar with past 5-6 years development in novel view synthesis in virtual augmented reality, you're probably very familiar with this work by Noah Snavely. A single view view synthesis using MPI multi-plane image. The idea is, if you can estimate the depth, if you can layer the thing into different depth layers, you're able to generate novel images taken from a novel perspective. So similarly here, what my student implemented is, well, let's train a UNet, what's so-called UNet, to estimate the height of every scene point. Once you have this height map, you can run that geometry projection and get some intermediate representation. Then you have another generator, which is similar to GAN network. The generator fixes those artifacts and make the image look like a real despite being a fake image. So that's the general idea, very simple. But the key obstacle, key challenge is we don't have ground truth height. If we had, that would be nice, it would be straightforward. So the only way we do this is close the entire loop, train this neural network end to end using the gas discriminator to tell whether or not your height estimation is reasonable. So in other words, this training is unsupervised training. It's end-to-end type of training. So I show you some results, I think complete my talk. I think I'm almost perfect, stay on time. So this is the first column, the first image some input. The second are the estimate height map. It looks crappy. I guess we haven't figured out how to better realize that, but the height roughly tells which part are forest, which part are ground. And this is the intermediate result after this MHI mapping. So, well, it's reasonable when the thing are above horizon plane, it becomes messy because you actually don't have that information from satellite image. While below the horizon line, it seems reasonable, although you see the artifact. And after GAN, this is what you get. Okay, if I don't show you this ground truth image, you probably find out this looks excellent. Well, you do see there's a road passing the image, and you do see the high trees. Of course, if you compare with ground truth, the trees are some what hallucinated. They are not real, but nevertheless, the height seems reasonable. And in particular, if your task is to localize based on the ground plane image, the road, they are quite matchable or matched. Some more image, well, this is, again, visualization. Input, first column. The third column is our output. The final one is the ground truth. the input and this and this. You see the bunch of tree here looks quite nice. And here, this is different about the row structure is same. Okay, so much for our method. How is this method compare with existing method, although there are not too many? Let me show you this slide. The input image is here, and the ground truth is the last column. Our estimation or prediction in the middle one, while the second column and third column are the result by pixel to pixel if you train on this cross-view image. And XFOC is another cross-view synthesis method. And you can compare these two and this or these two or these two. You find even the road structure are not preserved, while our method fit quite well. Okay. More result in build-up area, which tend to be difficult when you have high-rise building, or not high-rise, but build-up urban site. And quantitatively, our method is also best performing, and both the last two columns are our method, first best and the second best. They consistently outperform previous method. Okay, I must acknowledge some previous work, some related work, either prior to our method or follow up our work. Just in the interest of time, I didn't go into detail of their method. Just skip. Okay, just a quick summary right before 7:15 my time. So in this presentation, I briefly explain two of our works, although they are related. The first one is using cross-view matching, giving us satellite image and ground view query image. We can precisely pinpoint where your vehicle camera is and which direction the camera is looking at. We hope this can form interest baseline for future exploration. The second one is a simple extension. Since the main idea of the previous work is to inject human knowledge, we can use the same to hallucinate what it looks like from ground. Thank you for your attention. I'm happy to take questions.
Thanks for a great talk, Hong. I don't see any questions on YouTube. I'm going to ask a quick one in the interest of time. So how does something like this would work? You briefly mentioned urban cases, right? So I'm wondering, in a case very extreme like Manhattan, downtown Manhattan, where everything is a grid, will the localization method still work, or is it completely failing because everything is self-similar?
A great question. The short answer is unfortunately no, it won't work in high-rise area like Manhattan downtown CBD, but it works in most rural and suburban areas. Like in our city, there's no building higher than 6 levels. All the residential area, that's all fine. You have tall trees, you have up to 3-level buildings, that's all fine. For CBD high-rise area, the UCF group developed a similar technique, but using per building registration, per building matching. Is similar to landmark-based approach, although it's still in the cross-view scenario. So if you can identify this is the tower, you match with another tower. Yeah, a great question. Thank you.
Oops, sorry, I think I was muted. Yes, so yeah, thanks
So
again
I didn't
for
get
the
you, but I think I use up all the time.
yeah. Thanks for a great talk again, Hamdong. For the final talk of today, we have another speaker from Australia. So I also want to thank him for waking up early to be with us. And we have Michael Milford from Queensland University of Technology. And yes, looking forward to your talk, Michael. Please take it away.
Thank you, and thank you for the kind invitation. Let me just share my screen. Once you stop sharing, please. Hey, Vesely, thank you.
Is this okay now? Is it work? Yes.
Yeah, can you see my screen okay?
Yes. Yep, it works.
Okay, fantastic. All right, thank you so much for the kind invitation to talk. I know I'm the last, and so I will try and keep to time. One of the things I mentioned this to Hong Dong about being in Australia is we are typically either the first person to speak or one of the last people to speak at workshops due to time zone. That means you either get the first word in or the last word, which is an interesting experience. So today, in the brief time I have, I'll briefly introduce our group, talk about the sort of motivating challenge, although I know that's been motivated fairly well in today's various talks. I'm going to spend a little bit of time highlighting a couple of areas of work that we've done in this space, including going back a little bit historically and talk briefly about some of the areas that we apply some of this long-term localization work in. And finally conclude with some conclusions about, I guess, what we see as the major challenges and opportunities in this field moving forward, which hopefully are suitable as the final talk at the workshop. This talk is deliberately set up to complement a talk I gave a week ago at the autonomous driving localization workshop. It's great to see so many localization themed workshops at ICCV and in conferences. There'll be a little bit of overlap, but a lot of different work. So if you want the complementary set to that, what I'll talk about today, go look at that. And just a warning ahead of time, there'll be some mildly graphic content later in the talk, just in case you're a little bit squeamish. Nothing too bad. I just want to warn people ahead of time. So I come from the QT Centre for Robotics, or a large research centre at QT in Brisbane, Australia, with robotics and autonomous systems, doing all sorts of wonderful things in just about every environment, in the air, on the ground, on the surface of the water, underground and under the water. And localization is a key aspect of what we do in the centre. We do lots of research, bio-inspired localization, sort of modern learning-based localization, other projects, and a lot of applied projects in this space as well. If you want more information, look us up online. We have a lot of survey papers written by various members of the group, including collaborations with people you've seen today. And they give a sort of higher level, more detailed overview of some of these topics. And there's open source code for a lot of the stuff I'll talk about too. So to motivate it, and I'll move fairly quickly throughout the entire talk, we're talking about long-term localization, which brings with it many challenges such as appearance variation, but you can't explicitly decouple it from that other challenge that faces localization systems, which is viewpoint change as well. And these are really coupled problems. We know the world is always changing, its appearance is changing, and these are some of the problems that motivate much of the research you've seen today and more broadly in this field. Appearance change, lots of reasons why the environment can change its appearance, but is front and center one of the key problems in localization research. And this is the core problem. Places that are the same place in the world can look very different. The images in the column on the left are from the same place. Images from the same different locations in the world can look very similar. So we have all these challenging appearance problems to solve. And viewpoint change, which we're not talking about today, is another challenge, but it's often lumped in with appearance change. And dealing with both at the same time is sometimes pathologically difficult, but very motivating for a researcher. So we've been attacking this problem from a variety of different perspectives. I've got 7 different ways we attack this problem on this slide. I'm not going to talk about most of these today, but we really believe that a sort of multi-pronged attack on the problem that isn't just using the very big hammer of modern learning-based techniques is the way to make the most progress. And obviously, these are not completely separate techniques. Simulation, for example, plays a big part in many deep learning-based approaches. Physics can be used to bootstrap learning-based approaches. So they overlap, but they are also distinct as well. So I'll briefly mention some of the recent work we've done. So this is Stephen, Sorav, Ming, and Tobias's work on patched NetVLAD. It was good watching one of the competition challenge talks, which talk about various ways in which to improve on many systems, including patched NetVLAD. And the basic idea of this system was to take the very impressive original NetVLAD system, which still holds up remarkably well 6 years later, which is quite impressive. And instead of doing this at a global level, do this at what we call a locally global level. So we're not doing sort of small point features. We're not doing global representations of images. We're doing sort of local, large region-based representations. But the same overall process applies, plus a geometric verification step at the end to deal with the fact that you get a lot of noisy, spurious matches using this approach. And so this was published and presented at CVPR this year, and the results were quite good across a lot of the benchmark data sets. It's a very fast moving field, so you're only close to or state of the art momentarily, but we're able to achieve quite state of the art performances on some of these data sets. Also, these systems are notoriously computationally intensive to run, as roboticists are always interested in running these systems faster. And so the team came up with a number of different variants of our method that use a sort of cut down verification step called fast spatial scoring. And this was able to achieve, I'll show you the performance figures in the next slide, quite close to real-time performance. System was also robust to varying many of the parameters, like the size of these locally global features, which is coined as patch size on this slide. And here's the performance graph. So horizontal axis is seconds per query, basically seconds per single place recognition query. And you can see we're getting to competitive performance compute-wise with only a very modest reduction in recall at 1, which for many robotic applications would be quite acceptable and would be the only way to deploy it on a platform with limited compute. Here are some of the qualitative results. So these are all the standard data sets: Pittsburgh, Tokyo, Mapillary, Nordland. And it's great once again to see a growing number of well-curated data sets that researchers can test and evaluate their systems on in the field. One of the match examples from the Tokyo data set, just showing you the capabilities of the system. It's also able to deal with reasonable degrees of viewpoint change as well, but this workshop is focusing mostly on, I guess, appearance change. And it's open source, so it's getting a lot of love on GitHub. Go check it out, download it. It's reasonably well maintained by the team, who's doing a great job. Please feel free to try it out and have a go and send us your feedback. So I want to go back to some motivating work when we started in this field, which is dealing with this core appearance challenge. So when we attacked this problem about 10 years ago, started attacking it, there was essentially no visual localization or visual place recognition systems that worked particularly well on solving the problem in this slide, which is matching the places on the left, but not matching the places in the middle. So the only way we could initially solve this problem after looking around for other solutions was to use temporal filtering. So filtering data over multiple query frames. So this is a sequence SLAM approach. It's not actually a SLAM system. It was just a name we came up with at the time. But this is just to illustrate that some very simple concepts can take you a long way in this area. This is not precise 6 degree of freedom localization. This is topological place recognition under extreme degrees of appearance change. And the basic premise is very simple. You have a matching algorithm, and it doesn't actually matter what the matching front end is, as long as you have one. And what you do is you force your matching algorithm to find speculative matches for where you might be located in the environment within every local spatial segment of map that you have throughout the entire environment. Whether you're mapping a building, a campus, or an entire city, you force it to find hundreds of thousands or millions of these speculative matches so that every location in the environment has a match, a speculative match. Now, obviously, most of those are wrong. So to filter them, the idea was you filtered them by trying to find spatially and temporally coherent sequences of these matches. And it was this pairing of these two approaches together that enabled the system to match quite significant degrees of appearance change. Ironically, this was rejected from ICCV, I think with the bottom worst ratings you can get at a computer vision conference, which was sort of crushing at the time. But then it was resubmitted and won the best vision paper at ICRA the next year without any major modifications. And then it's sort of come around, and we've continued to work on this as have others over the years. And just to give an example, this is a paper Saurav Garg led, which is SeqMatchNet, which is being presented at Coral as an oral in a month or so. And the idea here is to combine modern, I guess, contrastive learning-based approaches with this core concept of sequence-based matching, and to actually link these together more organically rather than treating them as completely separate processes. And that gets you very nice performance in this domain. We also did some other bio-inspired work modeling other vision systems like that of other animals, or at least at a high conceptual level, and we were able to match places without having to use long sequences. Obviously, this is now a pretty easy problem with modern learning-based techniques, but at the time, this was the only way to do it in a real-time manner. All right, so that's just a little bit of technical stuff. I want to present some sort of more diverse approaches to long-term localization with the time I have remaining. There'll be a little bit of blood. It's not too gory, but it's just, I'll be covering a wide range of applications of what long-term localization can do for you. So this is the core idea of SequenceLam, which is essentially to find coherent sequences of local strong matches over multiple frames. The idea that is at the core of SequenceLam can be adapted very nicely to finding correspondences between different regions of images. And so this is what, if you just use SequenceLam or any other technique, coarse place recognition technique on a sort of whole image level, and you're trying to match places together, you can get significant misalignments. So you need some sort of way of locally aligning these images. And this is where I guess all the two-stage coarse-defined localization algorithms that are so dominant today in computer vision especially do a really nice job, because you get the initial coarse localization match and then you refine it. And so this is another version of that we did several years ago. And the idea is very simple. Instead of running SequenceLam over a sequence of frames as your car or robot or drone moves through the environment, you run SequenceLam on virtual sequences within an image. So you can see a visualization of this. You can see the virtual frames are reconstructed by taking paths or journeys through the image itself and taking out patches, or they can be any shape you want as long as they're consistent. And you do SequenceLam within the images, and this will give you correspondences between the frames. This is an example of the comparison or difference or confusion matrices you get with this approach for a sequence through the image, and you can then combine these in all sorts of different ways to create an overall hypothesis for correspondences between the two images. And then once you've got those correspondences, you run it into your image alignment algorithm or technique of choice. You're quite flexible there. So this is the first gory slide. So this is part of my motto of let no data set opportunity be wasted. And so I had some very minor skin surgery years ago on my head to get a cyst cut out. Sorry for the goriness. And what I wanted to do was show that these sort of techniques are very robust to sort of highly aliased, quite challenging visual conditions. So what we did was we logged data from the recovery of the wound over a long period of time. You can see this from just before surgery to 2 weeks after surgery, and you can run a technique like the one I just described to automatically align, not perfectly, but fairly well, this region over time. So long term in this case is the 2 weeks it took for the wound to mostly heal. And I'll talk about this concept of what we really mean by long term in the wrap up to this talk. You can also do another things who are interested in long-term change. So skin cancer monitoring, a number of people in the computer vision field have looked at this problem. This was our sort of initial sort of prototype. And once again, you're trying to track corresponding changes over long periods of time. In skin cancer case, it could be years, for example, and you might have to deal with multimodal data as well. Climate change is another one, and there have been some pivotal papers in conferences like CVPR and ICCV over the years. And so these are some examples of us taking data that's available online and doing alignment on it, where theoretically you could then follow up with quantitative analysis of what has changed in the environment. All right, so we work in a number of application areas, and a large number of these involve a localization component. I will only talk about one. Last week, I talked about the mining vehicles and autonomous vehicle projects that we've done. I'll talk about some fun research we did in collaboration with NASA JPL in the early days before they even had a 2020 rover. So this is led by James Sargent, but it was also in collaboration with researchers from the JPL lab. And the context at the time was long-term localization and tool point servoing for a rover. So the challenge context was simply that you might send instructions to your rover to drill, to target and drill a certain rock sample, but due to the sort of queuing of tasks, it might not actually execute that plan until many hours later. And during that time, conditions could have changed. So long-term could be several hours in this case. The atmospheric conditions might have changed. Lighting definitely could have changed significantly. The rover may have even shifted a little bit. So this is a long-term example that could happen within a relatively short period of time. The JPL folks were nice enough to give us a high quality synthetic data set simulating a number of the different sensing modalities that were expected to be on the rover at that stage. And we ran a very similar process to the one I showed you before, the sequence slam within images method, in order to generate the correspondences, in order to generate the servoing commands for the tool point. And so you can see the RGB and simulated pixel images from this data set. And you can see some of the correspondences the system is making. So we're doing sort of long-term image correspondence over the course of a few hours, but also multimodal sensory correspondence, so between RGB and simulated pixel images as well. So you can see this is in the lab. Obviously, we didn't have access to Mars. This is the actual visual servoing experiment that we ran, and we're doing it under very different lighting conditions to challenge the appearance invariance of the system. You can see it drilling in there and gradually honing in on the relative position that it was told to. Here are some snapshots. So you can see the lighting has changed significantly, shadows, lighting, color has all changed, but the robot was able to position itself fairly repeatedly at a fairly precise location, at which point in the real life scenario, it would then approach the rock more closely and perhaps drill it. We're continuing this work much more recently. One of the other areas we're working in is surgical robotics. Long-term in surgery is the 2 or 3 hours it takes, for example, to do a shoulder joint replacement operation. And during that time, a person is completely intact and then they're cut open carefully. You probe into their shoulder joint. There's muscle, skin, bone, blood, sometimes a bit of smoke. Other things that can obscure it. And so this is a very challenging, in terms of appearance change, thing to do localization in. This is just a mock-up in our lab. I'm not showing you footage from actual surgery, but you can see the sort of bone that we're trying to register and localize relative to over this long period of 2 or 3 hours. And this is work led by Morgan. All right. So I've raced through a sort of smattering of work that we're doing in this field. There's a bunch of other papers, including at ICCV and other conferences that I haven't covered today, but feel free to look those up. What I want to do is spend the remaining sort of minutes talking about some of the key thoughts and insights that we've had in our group. Hopefully these align with some of the other comments that have been made throughout the workshop. And these are usual disclaimer, these are just opinion. But hopefully they'll stimulate discussion following on from this workshop, maybe leading into next year's incarnation, wherever it is hosted. So the first one is this concept of long. So, and I know people like Torsten and others have been doing a lot of work in sort of trying to quantify these notions of appearance change. I guess in our perspective, the long is pretty much an arbitrary sort of concept. So what we really mostly care about, I think, is change. And so in sometimes long and change correspond to sort of multi-year timelines where a city gradually changes its structure, or in the climate change example, over 50, 100 years, a glacier would gradually change its position or extent. In other cases, like some of the ones I showed you today, it might be a few weeks in terms of recovery after surgery. And in more other cases, it might be hours, minutes, or even seconds might be long-term in terms of the appearance of the environment changing radically. And so I'd argue that what we really care mostly about is change, trying to quantify the degree of change. And so Torsten, the University of Essex, and a number of other groups have been doing a lot of great work trying to come up with a quantification for these sort of concepts. But I'd argue appearance change is also a little bit harder to quantify than related concepts of viewpoint change, where there's explicit geometry involved. And so these are some of the challenges I think we have as a field facing into the future. Another key concept is we need to work out really what we want our long-term localization systems to reasonably solve. So one of the great things about modern learning-based approaches is that they can be incredibly powerful, especially if you give them the right data and train them appropriately. But the downside of that is you can actually, it's not so much overtraining these systems, but exploiting their capability. You can get into situations where they are solving or being forced to solve appearance change problems that you might not actually intuitively want your system to be able to solve, especially if that system is then used in some sort of application where it's interacting with or being used by humans. Because if the system is sort of magically localizing itself in a way that no human could ever do, that's useful for some applications where safety is critical, but also it's not necessarily representative of what we actually want out of a localization system. And so I think it sounds like a sort of weird getting the problem back to front, but I think as we actually deploy these localization systems in actual autonomous systems more and more, we need to work out what we actually want them to be able to solve and what they should fail at. I think this is an area for further investigation. The parallels and analogies to the problem of viewpoint change are strong, but appearance change is not exactly the same as viewpoint change. So for localization systems, having techniques or methods or algorithms that have invariance to viewpoints, so you can approach a place from lots of different locations and still recognize where you are, that's very useful in a lot of applications. At the same time, you also want place recognition or localization systems that have a high degree of variance or sensitivity to viewpoint change. So one example of this is when you are localizing a vehicle to a specific lane, hopefully to sort of centimeter level accuracy. In some cases, you want to just know roughly where you are, and in some cases, you want to know exactly where you are within the lane. And in some of these situations, of course, you can use a coarse-defined localization pipeline, but in other situations, you just want a localization system that is very sensitive to you being in exactly the right place and rapidly changes its performance once you move 10, 50, 100 centimeters away from that place. So in viewpoint change, invariance and variance are both useful properties at different times. And so I'd posit the question in appearance change or long-term localization, is both invariance and variance useful at different times for your localization system? And I think that the answer to that is probably yes. But once again, I think this is a question that needs more thought put into it in terms of what we want out of our systems. The final point in terms of where this field is heading is the point that I made last week, which is no map or localization system exists for the purpose of being a localization system. Ultimately, it's there to serve a purpose, whether it's enabling you to navigate, whether it's enabling you to boost your object recognition detector because you know priors about the environment you're located in, whatever the task is, ultimately these systems have to be used. And I think benchmarks are fantastic and we should continue to use those, but we always have to be aware that these localization systems really need to be functionally tested. And we started on this journey a long time ago with long-term, quite challenging robot navigation experiments, where if the localization system failed at any time, it didn't just mean you dropped an extra 0.1% in your recall performance, it meant that your system failed and had to recover in some way. And so this is from IJRR, this is 11 years ago now. This is from IROS this year, work led by Dom and Toby on teach and repeat navigation. And once again, it's the same principle. The localization system's utility is constantly being evaluated because it's actively being used by a navigation system in this case. And this is not easy to do. It takes a lot more time. You can do some of it in simulation, but some of it has to be in the real world. But I think this core concept of functionally testing what the localization system gets you is key. And this will also help us evaluate the answers to the questions I raised previously, which is, when do we want these systems to fail? Because that's actually the sensible behavior. And when do we want them to be very invariant or variant in response to appearance change over long periods of time? So that's an overview of what I covered. It's a short talk, so hopefully some highlights there. Feel free to get in contact if you want to talk about any of these in more detail. Just a shameless plug, we have some big new projects starting this field running until at least 2027. We're recruiting large teams of many postdoc researchers, a large team of PhDs and other researchers in the positioning space, especially as pertains long-range, long-term navigation and positioning systems using both biologically inspired approaches, but also modern learning-based approaches as well. So please feel free to reach out if these sound of interest. And more generally, our group is very enthusiastically hiring. We have a huge need for talent at all levels, from undergraduate research assistants all the way up to professors. So please reach out and get in touch. So there's some image credits here. Hopefully this GIF slide doesn't cause too many fits in the audience, but thank you once again to the organizers for organizing this workshop. I hope that everyone has enjoyed it. And I think I've left a little bit of time for any questions or counter arguments to some of the points I raised at the end. Thank you.
Thanks, Michael. Thanks for a great talk. Yeah, so first of all, the last project seems very interesting, the multi-year project you said. So yeah, this certainly looks something we can keep an eye on. And the key thoughts were also very, very interesting. So I hope people got inspired from them. So I have a generic question about your work. So I've seen that many cases, what you do is you develop a generic method that's supposed to work mostly or mainly for localization, and then you move it on to other fields, like such as the surgery stuff and the things you presented, right? Is that something that comes naturally, and is it easy, or do you have to rethink parts of the methods and modify them? Is it plug and play, or it really involves more work?
That's a great question, and I'd love to speak about that for hours, but I'll try and be brief. Look, the first thing I'll mention is that in the brain, where we draw a lot of inspiration, there's a lot of evidence that shows that these neural circuits that are involved in spatial representation, so in localization and positioning and mapping, all the things we care about, are inextricably tied up with other aspects of memory. And so abstract concept encoding and recall, memory over time, all of these sort of concepts, there's a lot of evidence that shows that they intermingle with the spatial memory circuits in the brain. So we have this proof of concept that the actual brain probably combines explicit, tangible spatial coding with other sort of more abstract tasks. The second reason why we do this, where we start in localization and adapt it to other fields, is localization is as no one on this call needs telling, it's a beautifully concrete, relatively quantitative task. And so if you're going to start anywhere trying to create these fundamental capabilities, it's the best place to start. And then you move into these more abstract, maybe a little bit more fuzzy domains. And so I think in terms of order, I think this is the right way to do things. But the hope is that as you apply these systems, this is the link to function that I kept talking about. As you apply these systems in other domains, you then learn interesting, unexpected insights about the core localization system you developed, and then you can close the loop and further refine it. So that's the idea. It doesn't work that way always, but when it does, it's a beautiful thing.
Okay, thanks. Yeah, that's certainly a very interesting way to motivate the whole discussion. Any last questions before we end for today? I don't see any more questions on YouTube, so let me quickly share the final slide, which is just the ending slide. And thanks again, Michael, for the great talk.
Thank you.
And also thanks everyone for joining. I want to thank all the presenters, the challenge participants, and the invited talks were all great and very interesting. And I think that's it for today for this version of, actually the fourth version of the long-term localization workshop. And I hope to see everyone in a future version of the workshop. Thanks everyone. Goodbye.